What we have here is a transfer function in the Laplace domain. So the S stands for the Laplace domain. And what we want to do is transform this one into an impulse response, which is a function of time. So in the t domain, the time domain. And what we want to do is use these equations to transform something from the Laplace domain to the time domain. So we want to shape this thing into a form that can be represented like this. And then we can easily transform it to the time domain using the inverse Laplace transform. So what we're going to do now is write this in another form, namely the form that is presented here. So we want something in like this, or something like this, or something like this. And how we're going to do that is by looking at the denominator here. We have a denominator s plus 0.1 and a denominator s plus 0.01. We also have a 1 in the front here, so that's something we're going to count as well. And you can see that these two are almost the same. So we're going to do a proposal for a solution. Namely, we're going to say that this could be equal, and we're going to figure it out if it is, to a times 1, this one. So we can transform it into a delta function, plus b times 1 over s minus a, and we're going to choose this as an a. So s plus 0.1, this is minus 0.1, plus c times 1 over, we're going to do the same thing here, s plus 0.01. These letters are coefficients which we need to solve for so that our old transfer function is equal to our new proposed transfer function. So right now, we don't know what the coefficients are, so we don't know if this is equal. So what we're going to do now is write this in a form that is the same as this one, so on the same denominator. I'll do that right now. You can pause the video right now, or you can follow along. So what we did here was write this expression on the same denominator. So we multiplied a by this, b by this, and c by this. And this way we can put them all on the same denominator. And now we can, if we look at the original expression, we can say that this cancels out. So this is h of s, transfer function. So these two cancel out. And now we got to say that the denominator of this expression needs to be equal to the denominator of this expression. So how does this look? I'm gonna delete this for a second. Okay. A times s plus 0.1 times s plus 0.01 plus b times s plus 0.01 plus c times s plus 0.1. This needs to be equal to this expression here. So 4 times s plus 1.77 times s plus 0.087. Okay, I don't have enough space here. Let me fix this. Now what we're gonna do is fill in a couple of points, like s equals 0, s equals 0.1, s equals 0. It can be literally anything, but you can save yourself some time by choosing the points wisely. Let's take, for example, s equals negative 0.1. If we fill this in, in the right-hand side, we see that this factor becomes 0, so everything here becomes 0. So the coefficient a doesn't really matter here. And then if we look at this side, this also becomes 0. So the coefficient c also doesn't matter. The only coefficient that we have is b, because this doesn't cancel out. And then we fill in negative 0.1 on this side, and we get a value for b. And we can repeat this process for a, b, and c. I'm going to show you this for s equals negative 0.1, and I'll leave it as an exercise to find the coefficients a and c. So let's fill this in. We have 4 times negative 0.1 is plus 1.77 times negative 0.1 plus 0.087 is equal to, this became 0, this is also 0, so only the b times negative 0.1 plus 0.01. So if you type this in, in a calculator, we find that it is negative 0.08684 equals negative 0.09. I have to look it up here on my calculator, times b. So when we rearrange it, we write this to that side and divide it by it. B will equal to 0.965, around about that. So that's B. And so for the other coefficient, you could think about what values you would set S to. And for C, for example, you can pause the video if you want to think about it. It would be negative 0.01. Because if you insert this value here, this will become 0, this will become 0, and this will be a value, this will also be a numerical value. And this way you can find C out of this. And then for A, so I'll write it like this, S equals negative 0.01. Here we find C, coefficient C. And then for A, there isn't really an easy solution. You can you can pick the point s equals 0.5. You can pick the point s equals 10. You can basically pick any point you want, and you use the values you found for B and for C to find A. So if you can imagine this expression again, we have S, we have chosen a value for S, and we have found already a value for B and C. So the only unknown here is A, and so we can solve for A. And now we have A, B, and C. I'll give you the values from for A, B, and C. So C became 6, and A became 4. Now if you insert this here, we have a new way to write our transfer function with these coefficients. So h of s equals 4 plus b times this one. So that's 0.965 times 1 over s plus 0.1 plus, and then c comes into play, 6 times 1 over s plus 0.01. And this is something we can use the inverse Laplace transform on to find the impulse response. This is how we do it. We made sure in the beginning of the video to write our new transfer function as something we can use the Laplace transform on. So what we will find is, I'm going to give myself some space again. what we will find is, now using the inverse Laplace transform, that h of t in the time domain equals 4 times 1, so that will be 4 times the Dirac impulse, plus b times, or 0.965 times, 65 times e to the at, and the a here stands for negative 0.1 t, and then plus 6 times e to the negative 0.01 t. And there you have it. This is our impulse response.